Okay, hello to everybody. We will start this, what we are calling internally a scientific roundtable. As organizer of this roundtable, I will do a small introduction, but I have decided not to take a place in the table, in the not round table, just to allow panelists to have more time, and there will be less people talking. So I have, so Sébastien Chambaud will be taking, Professor Chambaud will be taking the role of moderator of the table in my place. At this moment, I think that it's pretty clear the aim of this meeting. I would describe in my own words as a threefold aim for this meeting, which is to promote artificial intelligence as a tool in mathematics oriented to application, to promote a debate in the mathematical community about usefulness and convenience of artificial intelligence as a tool for applications of mathematics, and also, and last but not least, to explore the current mathematical challenges in artificial intelligence, or said in another way, which should be the contributions that we as a community could and should provide to the artificial intelligence world. And I am explaining this because this session, this roundtable, has been organized with this aim to make a contribution in these lines that I was describing, or in this, I would say, I would like that it be a philosophical contribution, and with the hope that at the end to be able to derive some written conclusions about concrete actions and homework or take home homework to do in the future for everybody as a community. So this is my introduction. This is to explain what we are doing here at this moment. I think that now it's moment to thank everybody for being here. I mean, you audience, but especially to the panelists. This is we have put on their shoulders a very strong task, which is to provide insight in the directions I was saying, and this should be acknowledged, I think. So about how the roundtable will work. As I said, I will, despite of the fact that I am organizer of this table, I will not be participating to allow more time for discussion, although I am stealing a little bit of time with this introduction. But to say that each panelist has been assigned a role related to her area of expertise. And we expect we have been asking them to do a contribution in a certain direction. And there will be also some questions. And we hope that at the end there will be a rich debate. Joan Bruna, because of schedule reasons, he's currently in New York, will be participating in a video that it was recorded at the end of last week, asking some concrete questions. And since, as I said, the last thing I will say is that since I have delegated the moderation to be the chairman of the roundtable to Professor Chambaud, I should introduce him to avoid auto-introductions. He will introduce the rest of the panelists. So Sébastien Chambaud is emeritus at the Polytechnic University. He has taught everything related to algebra, geometry, and some areas in computer science like error correcting codes. For me, it's very important that he has made very important contributions to applications of mathematics and also to mathematics oriented to applications. I am very careful in this terminology because in this country we use too much the terminology applied mathematics, and it has somehow lost the meaning. So, last thing about Professor Chambaud is that he got recently two prizes. One is from RESME, and this is a prize pro meritis at Mathematica Martem Expectantibus. So I am explaining this because I wanted to read this sentence, essentially. And also the Narcís Monturiol Medal to scientific merits delivered from the Generalitat de Catalunya. So I think that he is a very good authority in taking chairmanship of this roundtable. I stop here and I leave the word to Sebastián. Thank you. As I said, thank you for being here and participating in this roundtable.
Okay, good morning. Thank you, Luis, and welcome to the second roundtable of the Congress. I like both the bridges and particularly the new bridges between mathematics and data science. Can you hear me better now? Thank you. I'm going to just go through a few slides to give some context from my point of view of what the roundtable should be. I think that Luis already told you about the targets of this roundtable. You have them in the screen. So yes, we are all here to see this relation between data-driven computational mathematics by looking at the thematic evolution of the mathematical contributions oriented to applications. To prospectively think and discuss about the challenges, open problems, and strategic lines in which mathematics can contribute to the foundations of computational mathematics, artificial intelligence, and their algorithms. And the third point, I think, is the most important, because it's something that we should do together, which is collectively come up with specific initiatives, policies, and detailed actions proposals to help interested mathematicians, of course, but most importantly, young researchers in contributing to the foundations of artificial intelligence and data-driven computational mathematics. I have taken 3 slides that come from a paper written by, you have it on top of the screen, the Artificial Intelligence Watch. The number 1 is the reference at the end. When the slides are put on the web, you will see the document, but it's very easy to find it, because if you write AI Watch document or documents, you are going to get it immediately. It is an important point. In any case, you have here an artificial intelligence taxonomy that has some, what they define, this committee, what they define as core lines of work and transversal. So you have, and if you look at them, you are going to see that all we have been talking here and what we may be talking in the next days or years, I think has much to do with our role as mathematicians. For example, in reasoning, knowledge representation, automated reasoning, common sense reasoning, in planning and scheduling, searching, optimization. The plenary lecture today has been basically on that, on an aspect of that. learning, machine learning, communication, natural language processing, computer vision, perception, computer vision, audio processing, and then in the transversal part, integration and interaction, multi-agent systems. This notion appeared in the last talk. Robotics and automation, connected and automated vehicles. This is coming. It's already here. Services, artificial intelligence services, and ethics and philosophy. I think that anyone should be welcome to express their views about how ethics should be preserved in the evolution of artificial intelligence, and philosophy of artificial intelligence, which for me it's okay. Now, this, in an exhibit, that imaginary exhibit in my faculty, there is a module about artificial intelligence, and I have taken this scheme, which is nothing but what I already told you, but in a graphics mode, so that any one of you can look at it and see to which part you'd like to contribute. In particular, to contribute in view of proposals of this roundtable. And since this scheme is according to application domain, and there is a scheme about techniques, roughly speaking, used in the field. Now, having said that, I think that we should also care about the natural intelligence for the future, not only the artificial intelligence. And in this, it is a pleasure for me to present this slide, which is prepared by the McKinsey and Company, defining the skills citizens will need in the future world of work. This, to future-proof citizens' ability to work, they will require new skills. But which ones? A survey of 18,000 people in 15 countries suggests those that governments may wish to prioritize. So therefore, I guess we may be aware of this and just push the wind toward the direction that it should go. You can find this at the bottom right of the screen. You have the mckinsey.com, where you can find this. Now, I will not go into detail of this because you will have later time to look at it, but they group the skills in 4 groups. In this screen, you have 2 groups, one called cognitive and the other one interpersonal. I think that we should be happy to learn that in the cognitive skills, critical thinking is a must. I think that in mathematics, we try to teach and to train people into critical thinking, structured problem solving, logical reasoning, understanding biases, seeking relevant information. And then, well, this is one part of this. The other one is communication, planning and ways of working, and mental flexibility. I do not know how these skills today are represented in our curricula, but probably there should be some thinking about this. There are interpersonal skills. These usually, I think, are assumed from everybody. And in the next screen, you have self-leadership. Again, this is self-propelling oneself into learning to learn, and so on. And then there are digital skills, digital fluency and citizenship. Again, I think this should be relevant in our curricula. Digital fluency and citizenship, fortunately, the young people are already fluent on that, very fluent. So I think that here we are on a winning path. All this means digital literacy, digital learning, digital collaboration, digital ethics. For the people of some age, this may be a little bit new, but it shouldn't be new for the new generations. Software use and development, programming literacy, data analysis and statistics, computation and algorithmic thinking, and understanding digital systems, data literacy, smart systems, cybersecurity, literacy. We are going to learn about this more today from Ilaria Chilotti, and text translation and enablement. Well, this is just, my idea is that for the debate, there should be inputs from everywhere so that we can make progress toward powerful conclusions of this roundtable. Now, one thing I did, or we did with Luis, is to prepare a list of questions just to send them to, first of all, to the panelists, but then also as a stimuli for you to contribute to the discussion. And I'm just going to read them, just in case you cannot see very well. 1, in what sense is data science a science? 2, these questions could be modified, could be enlarged, anything that this meeting can propose. 2, how do you see the relationships between data science, machine learning, and artificial intelligence? 3, and the relations between artificial intelligence in general and the neurosciences? 4, what mathematical techniques are used in the above disciplines? 5, are we moving toward more interdisciplinarity, particularly within the research groups? 6, in what forms could research in teaching in mathematics take advantage of the current and future developments in artificial intelligence? Will it be like the advantages of using computer algebra systems in the last 5 decades, or something quite different? 7, in what fronts could research driven by mathematics contribute to the advancement of artificial intelligence? 8, can we go on with the curricula as understood today, or should we consider and anticipate whether it would be convenient to modify them? If so, what sorts of modifications should be undertaken? 9, what should be the role of mathematical research institutes in defining a suitable strategy for productive relation between mathematics and artificial intelligence? And 10, what should be the role of mathematical societies, academies, faculties, etc., in driving the changes deemed necessary? And I'm going to add a number 11, which is not written here, which is, I think it's very important when one looks at the diaspora of talent we have in this country, how to attract talent and keep this talent productively in our organizations, in our research groups. Now, this is as far as the general introduction I wanted to tell you. Now, I think it's time to present the other panelists. One is Joan Bruna. Since I introduced him in the plenary lecture, I will not repeat it today. It will be the first thing we are going to listen to. It's a video, a sort of a dialogue video we registered last week, just because there is this time difference with New York. Next comes Ilaria Chilotti. Thank you very much for accepting being in this roundtable. Ilaria Chilotti obtained her PhD, from the University Paris-Saclay in what used to be the Université de Versailles Saint-Quentin and Yvelines in 2018, under the supervision of Louis Goubin and Nicolas Zama. Her thesis concerned the study of fully homomorphic encryption, FAG in acronym, fully homomorphic encryption schemes, a domain on which she is now a recognized expert. Notably, during her PhD, Ilaria co-authored the scheme Torres Full Homomorphic Embedding, currently one of the fastest homomorphic encryption schemes in the world. You will learn a little bit more about this fully homomorphic embedding later in her presentation. She is the author of several publications, remarkable publications. Among those, she won the Best Paper Award at Asia Crypt 2016 for the paper introducing the Torres full homomorphic embedding. This paper was co-authored by other people. In 2019, she was part of a team that participated to the I-Dash competition. The competition counted 4 tracks, each one with the goal of solving machine learning problem on genomic data by using a specific technology. Ilaria and her team obtained the first place of the fully homomorphic encryption dedicated track. The track counted 54 participant teams from all over the world, and only 6 of them completed the task within the time limit imposed by the competition. Ilaria also contributes to open source development of fully homomorphic embedding technologies. She not only contributed to the Torres full homomorphic embedding, multi-key Torres fully homomorphic embedding, and concrete libraries that are accessible at the GitHub. After her PhD, Ilaria worked at Microsoft Research in Redmond, USA, as an intern, and in the COSIC research group, which is Computer Security and Industrial Cryptography Group, which develops advanced cybersecurity solutions to protect data in the cloud and in the Internet of Things, and to protect the privacy of users. So, as an intern and in this group, at the Katholieke Universiteit de Leuven, or in French, or in Spanish, Universidad Católica de Lovaina, Université Catholique de Louvain, as a postdoc. Ilaria is currently working at Zama, a French startup developing homomorphic encryption-based solutions for secure computation on the cloud, where she is the director of research. In a recent paper of her, we read, "Our results indicate for the first time that deep neural networks are now within the reach of fully homomorphic encryption. Importantly, in contrast to prior works, our framework does not necessitate retraining the model." Now, in the case of Jesus Maria Sanserna, I think that it's very well known here in Spain, but nevertheless, I think I will read a short bio of him. He is full professor of numerical analysis at the University of Valladolid since 1982, and rector in the period 1998-2006 of this same university. And since 2014, he holds a chair of excellence in the Universidad Carlos III of Madrid. And since 2018, he is the president of the Real Academia de Ciencias Exactas, Físicas y Naturales, or Scientific Academy, which is a public institution dedicated to the study and research of mathematics, physics, chemistry, biology, and geology, and their applications, as well as their promotion for the benefit of society. He was elected as full member in 2007, and his discourse was on geometric integration, the name he coined for the fruitful area of research he pioneered. He has been invited as speaker at more than 100 international conferences, including the International Congress of Mathematicians, the ICM, in Zurich, 1994, and the International Congress for Industrial and Applied Mathematics, the ICM, in Beijing, 2015. He has been editor of many journals, and is still editing many journals, including the SIAM Review and Numerical Algorithms, both these last two, since 2012. I finish with a quotation from an interview in the Portal I Math of 2007 that says, "No other science permeates the other sciences as much as mathematics does." After these introductions, I think that we go on with the table by listening to the video, this dialogue video with Joan Bruno. Good morning, Joan.
Good morning.
Well, due to the time difference between New York and Valladolid, we have agreed that it would be more expedient that your contribution to the debate roundtable be in the form of a pre-registered dialogue rather than a monologue. Your answers will be a much welcome contribution to the aims of the roundtable and to the outcomes that we shall produce. So let's start. In what fronts could research driven by mathematics contribute to the advancement of artificial intelligence?
Okay. First off, thanks, Sebastian, for having here, and I'm sorry that I cannot be in person. I hope you're going to have a very profitable and enjoyable roundtable. So, okay, so to your question, Sebastian, I guess first it would be what do we mean by artificial intelligence? I guess that now this is a word that is used more and more outside the scientific circle. So I guess that if if you take a very broad definition and you think about AI as a general technique to extract information from data that come from the world, I guess that mathematicians and statisticians have been doing this for many centuries, right? Even like Gauss and Legendre already learned how to do linear regression. So I guess that my answer would be that if you take this thing at large, I mean, math has been contributing to AI since the very beginning. And it starts from very basic foundational statistics, but also goes to game theory, image processing, and even, let's say, what we now understand as the modern foundation of machine learning, the statistical learning, is really done at the roots of basically high-dimensional statistics. And so more recently, I think that if there's something that I think is new, a bit more, that has happened in the last years, is that machine learning has really put forward this very fundamental interplay between kind of the statistical and the computational thinking. So really putting the emphasis on algorithms. And so I think that, again, this is not something that is like strange, or I think mathematicians have also been thinking about computational questions. For example, if you go into the fields of optimization or numerical analysis or even harmonic analysis. And I think that even like just to complete in terms of applications, if you think about more AI as something that is more like in contact with real world and real applications, I think there's also like huge opportunities, especially in computational science, for example, computational biology, chemistry, physics, etc. So again, applied mathematicians have been, I guess, pioneering, paving the way. Like applied mathematics as a field was, I think, born and exists for that purpose, right? To bring mathematics to the purpose, right? To bring some leverage the tools of mathematics to solve real problems in PDEs, in computational physics, etc. So I think that at the end, my conclusion is that research driven by math has been, will be, and is being actually a major driver for AI, and I really think it's going to continue like that.
Okay, we're fine. Now, the second question will be, are we moving toward more interdisciplinarity, particularly within the research groups?
Well, I guess it's hard to say in general. I think that the research group people, like researchers working in AI, if you take it very globally, there's a huge diversity. I think that, I mean, I can mostly speak from what I know more, which is the research that really lives at this intersection between theory and applications, in particular in machine learning and deep learning. And there it's obvious that the answer is yes, right? That now the students who come and work in these topics, they have a skill, they have a total, like very broad control and skills across, like, algorithms, implementation, but also they need to be very strong in different areas like statistics, probability, analysis, optimization. And so these, in that sense, yeah, these are problems, topics that are really at the crossroads of many disciplines. The other thing, of course, is that machine learning is still in a clear expansion phase, right? So like the field is growing in researchers. So this means that naturally many researchers that are in neighboring disciplines join, and this is very natural drive for interdisciplinary research, right? Just because we have more and more colleagues that start to get interested in these techniques. And so that's, I guess, another way to think, to say the same thing, right? That it's, yeah, indeed, it's becoming very interdisciplinary because it's an expansion phase.
Okay. Now, in what forms could research in mathematics take advantage of the current and future developments in artificial intelligence? Would it be like, say, the advantages of using computer algebra systems in the last 5 decades, or something quite different?
Good question. I think, in my view, the current advances in AI and deep learning, in particular, are perhaps one of the best gifts that you could give to a mathematician, right? In the sense that these are a set of algorithms and results that people care about, and that really go against the folklore wisdom that several problems in high dimensions are hard and cursed, right? So there has to be a reason why these algorithms work, and we have to find this reason. And as of course, my colleague, much more wiser than me, Ingrid Dobeshi, she wrote this here in a recent interview with New York Times. If we understand this reason, we are going to go much farther than if we don't understand the reason. And I see this as almost like our duty, right? I mean, I think this is really like the North Star that we should be following. And I think that clearly along this process, right, like working on these problems, it's going to clearly open new disciplines. It's going to create new fields. It's going to create new connections. And so I would really see that, yeah, that in this context, the back and forth between mathematics taken as a discipline, and AI or machine learning, it's really go right. We can produce as mathematicians foundations and guarantees, and maybe optimize some of the results that have been obtained in the area. But I think it also goes the other way. So these applications are generating new questions, and these are going to be, I guess, it's going to be an adventure to try to understand them.
Perhaps my question also contains the idea of whether there are going to be computational aids driven by artificial intelligence technologies to help mathematicians in their work.
Okay, I wouldn't be able to say that. I don't know much about this topic. I know that there's indeed some interest in like theorem provers, automatic theorem provers, and things like that. That can be that this could help. But yeah, I mean, I think that in mathematicians who have been developing and interested in these areas, they already have been developing their own tools, right? So I would not. Yeah, I'm not sure. I'm sure that there's people who know more about this topic that can comment more. But yeah, could be interesting.
Yes, we'll try to find out. Now, another question. Can you describe in broad terms what mathematical techniques are used in data science, machine learning, or artificial intelligence in general, or even in the neurosciences?
Yeah, I mean, there's a, I guess that the mathematical techniques that are involved in these topics really span, on the one hand, like mathematical statistics. So these are the questions of, understanding optimality and consistency of certain statistical estimators, right? So when can we certify that we are learning certain structures from the data, and maybe how efficiently we can do that. Then there's, of course, disciplines that involve probability, like in particular high dimensional probability, that really tries to understand the difference between solving a problem in the worst case, which can be very hard, versus solving it in the average case, which is the traditional setup in which we typically evaluate machine learning. And so there's also questions about optimization. So optimization is concerned with the question of solving, like finding critical points or optimizing functions also in high dimensions under different assumptions of different regularity assumptions on the function. And so this is also like a very, I would say, well-established mathematical discipline that is now gaining a lot of traction, a lot of presence in the field. There's, of course, analysis, which is concerned with ways to approximate functions in high dimension, and how these questions express themselves in presence of high dimensional structures. There's also, of course, very important mathematical disciplines that are at the core also of modern machine learning. For example, signal processing. Many of the applications that we are interested in machine learning, they involve data, but this data has a very natural physical structure, right? It's typically signals defined on a certain domain. So like all the mathematical disciplines that come with understanding signal processing, in particular harmonic analysis, are also very important. And then also other, I think, disciplines that recently we have been using in the field that are also, of course, becoming more and more important are, for example, statistical mechanics, which is concerned with understanding the evolution of large systems, right? In that case, think about like a neural network as it trains as a system that is evolving. So tools from statistical mechanics to understand these dynamics. And also, as I said before, I think that the theory that is really at the interface of mathematics and theoretical computer science, like complexity theory, is also a field that is has a very important role to play in developing the foundations, right? It's really understanding fundamental limits of algorithms, right? Which are the statistical questions that we ask that are fundamentally impossible to solve versus those that can be efficiently solved.
Excuse me. We discussed not long ago that in the limit, the dynamics of a neural network is approximated or is driven by an ordinary differential equation. Can you say a few words about the importance of this way of looking at the matter?
Yeah, I think it's so the importance, I think, it as in relation to what I was saying before, is that if you want to understand when and why machine learning or deep learning works, this question has to be asked, I guess, at different levels, right? So first is this question of, does it always work, or does it work for typical problems, or does it never work, right? And so depending on the level in which you ask the question, you have to use different tools, mathematical tools. And so this, as I say, like this formulation of neural network training in terms of this like mean field or like very large system of particles, right, and trying to understand things that happen at the typical case, it's an important tool to understand this question in the average case, right? And I think it can provide some qualitative understanding of why this thing works, right? And I say qualitative because these approximations, right, as you all know, they are really based in the limit, right? So they become effective in the limit when the system has many particles, right? So it's not, in the sense, it's not necessarily like an algorithmic answer, right? To how many operations do I need to learn this function, but it provides like a very sharp and I would say like clean mathematical picture that is true qualitatively, right? When the system is large enough.
We are speaking about data science, for example, and I would like to ask you, what is your view of what scientific standards should be applied in the research in these fields?
Like the scientific standards. Well, I guess that we should be taking data science like with the highest scientific standard, right? And I think that's the aim. And so I think, yeah, I mean, data science, or we could even call it in plural, like data sciences, they are really concerned with, I guess, like their mission is to understand when, how, and why we can extract information from data, from measurements, and they are really concerned. I mean, there's of course a methodological aspect of developing algorithms, theorems, and guarantees when this can happen. And this is, I think, subject to like the typical standards of rigor when you do mathematics, right? And when you develop algorithms. But then there's also other layers, like other aspects that make data science such a rich and an interesting field. Is that there's also like social science. There's also application areas. For example, when we apply these algorithms to, let's say, neuroscience or cognitive science or computational biology, we are faced with new layers of questions and new layers of results that also come with their own standards. For example, now there's a lot of interesting efforts in understanding, for example, ethical considerations about machine learning algorithms. So these are all under the umbrella of data science. And I think they all subject to the same scientific rigor as traditionally has happened in these fields, right? In particular, everything that involves some kind of statistical analysis.
All right, thank you very much. And I hope that later you will also learn about the other contributions to the roundtable.
Yeah, of course.
So we can put that together. Thank you very much.
Thank you very much. Bye, Sebastián.
Bye-bye. Well, now we are going to the talks. Yes. Now it's the turn of Ilaria Kellotti.
Okay. Can you hear me? Yes. Hi. I would like to start by thanking the organizers and Sebastian for the invitation and for the nice introduction you did before. So today I'm going to talk about Fouriomorphic encryption. So I give you my opinion as a cryptographer. And especially I will describe to you this very, very nice and new technology we're using in the company where I work. Okay, so to describe you the technology, I would like to start from a real world scenario, which is actually very, very realistic nowadays, where we have a user and the cloud. So the cloud is this very blurred entity that is represented by servers located somewhere in the world that offer you the possibility to store your data or to manipulate your data, do the computation, offer you services to analyze your data or whatever. So, of course, when it comes to data, cryptography tries to protect this data, and especially classical crypto allows you to protect the data during the communication. So this means that when you will send your data to the cloud, you will be able to encrypt the data. So whatever attacker or person that tries to learn about your data will not see anything but an encryption. So the communication is protected by crypto. But the problem is that when the data arrives in the cloud and you ask the cloud to manipulate it, to evaluate functions on it, the cloud needs to decrypt the data. And so it will see your data in clear in order to evaluate whatever function service it needs to provide. And of course, since the communication is protected, it will send you the data back encrypted, and you, the user, will be able to decrypt and see the result. So this might be a little bit annoying, especially when the data that the cloud is manipulating is sensitive. So when I talk about sensitive data, I think about medical related data, economic, financial, I don't know, your medical exams, your tax information, and so on. And in this case, we don't want the cloud, because we might not trust the service to access the data in clear. And unfortunately, with classical crypto, in order to be able to manipulate the data, the cloud needs to access this data and see it in clear. So fortunately for us, cryptography evolves and proposes a new solution. And this new solution, among the others, is called Fouriomorphic encryption. So very roughly speaking, Fouriomorphic encryption is a technology, an encryption scheme that allows you to, of course, encrypt or decrypt your data, but also to manipulate the data when it's encrypted. So this means that if our users want, as instance, to ask the cloud provider to run an algorithm to detect, I don't know, a mutation in his DNA, she can fix a secret key that she will keep secret, and she will use it to encrypt her data. So she will send, as before, the data encrypted on the cloud. But this time, if the scheme she's using a Fouriomorphic encryption, the cloud will be able to evaluate the existence of the mutation in the DNA without the need to see the data. So it can do the operations on the data encrypted. So the result, of course, is going to be encrypted as well. It will be sent to the user, and the user, which is the only owner of the secret key, will be able to decrypt it and see the result. So again, I would like to stress on the fact that with this technology, the cloud doesn't see anything about the client's data. It learns nothing about the client data. The information it's treating is always encrypted, so gibberish, if you want. Also, there are two other points that are very nice with homomorphic encryption. The first one is that there are no data breaches. And the reason is that even if an attacker accesses the cloud, the server, it will find only encrypted data. So it will not be able to access the private information. And this is actually a very common problem nowadays. We have heard about many data breaches and many data losses. And again, with homomorphic encryption, this might be prevented. And also the server location, the physical server location, will not be relevant anymore. So why I want to stress out on this? It's because every different state in the world have different privacy regulations. I don't know if you heard about the GDPR regulations in Europe to the protection of the privacy. Very nice. But in other countries, there might be different privacy regulations or even none. And so where you send your data will affect the way your data will be treated and the privacy that will be considered on this. So fully homomorphic encryption existing schemes are based on a hard problem, which is called the LWE, and it's a lattice-based problem. And a nice thing about this LWE problem is that it's post-quantum, so it will be resistant to quantum computer, very roughly speaking. So the technology is very nice, allows us to have a very nice solutions. And at Zama, the company where I work for, we're trying to provide this homomorphic encryption and make homomorphic encryption be accessible by anybody potentially. So the startup has been founded in 2019, late 2019, by Pascal and Rand, which are our CTO and CEO. Nowadays, we count 32 people in the team from 8 different nationalities, and the people are very different type of specialties. We have PhDs, so researchers. We have also PhD students that are doing their PhD with us, and we have engineers and developers. And so we do at the same time research, which is important because we are an innovation startup, so we need research, and we also develop our products. And we're based in Paris, and our mission is to develop, as I said, homomorphic encryption solutions in order to make the computation on the cloud secure. So just a few words on homomorphic encryption to give you an idea of the operation we can do. So the scheme we developed at Zama is the TFHE scheme on which I worked during my PhD and afterwards. So the operations we can do are quite basic if you want. We can do additions and constant multiplication. So this means that if you have encryptions of data, well, you can add homomorphically the encryptions, and the result is going to be a new ciphertext encrypting the addition of the two messages. Or you can multiply with a known constant. So in this case, A is the known constant, X is encrypted. The result is going to be the product of the two. So again, to do those operations, you don't need to know any secret. Anybody can do them, even somebody that doesn't have any information about the messages. Something happened? Okay, great. So something that is important to know is that in the ciphertext, and I will say it like without entering into details, in order to assure security, there is some randomness inside the ciphertext. So this randomness is measured in my slides with those little thermometers that you see next to the ciphertext. And when you do operations, this noise grows. And if it grows too much, the result is going to be compromised. So that's why it's very hard sometimes to do many operations in homomorphic encryption. But thanks to a cryptographer in 2009, there was a solution proposed, which is called bootstrapping. And in TFHE, we have a variant of the bootstrapping, which is called programmable bootstrapping, which is an operation that allows you to reduce the noise. So the noise that is too big will be reduced to a fixed amount. And at the same time, to evaluate a univariate function. So you have an input X, you have this univariate function represented by a lookup table, and you will be find as an output f of X. So the evaluation of the function on the input. So what is nice with those operations is that by using addition, constant multiplication, and univariate function, especially with the PBS that takes care of the noise, but you are able to build any possible circuit, to evaluate any possible circuit. And a very nice application to using those free functions, free homomorphic operation, is the inference of neural networks. So I would like to, I will hope like the expert in machine learning will pardon me for putting many things under the carpet. So a neural network is something that looks like this. We have many layers in more or less layers. In every layer you have neurons and they are connected. They take an input, they will evaluate this input, extract features and so on to give you an answer to the question the network is trying to answer. And the question can be very wide, like, I don't know, just to recognize and written digits or distinguish between the picture of a cat and a dog, to very complicated problems like, I don't know, seeing an X-ray, detect if there is a tumor in a certain organ of your body. So the neurons look something like what I'm showing you in the slide. They're this entity taking various inputs that can come from the input layers or previous neurons. And what the neuron does is does initial linear combination by using some weights and biases coming from the description of the network. And then it passes this result to an activation function. And activation function can be very different functions, so generally nonlinear functions like ReLU, sigmoid, or hyperbolic tangent. So in homomorphic encryption, we evaluate this, all of this homomorphically. We encrypt the inputs, and we evaluate the linear combination by using the addition and the constant multiplication, and the function, the activation function, by using the PBS, which evaluates a univariate function. And the result is going to be not noisy or less noisy because the PBS has taken care of the noise. And so potentially we can compose this neuron one next to the other in order to evaluate neural networks, even very deep neural networks. So we did some experimental results in the company, and we tried to evaluate deep neural networks with 20, 50, and 100 layers. So the 100 layers is not a limitation. We can go even deeper, but these are just preliminary results. And so that's what it is. So we did experiment by keeping very good levels of security, especially 128 bits of security, which is the standard for homomorphic encryption. And we showed that we can evaluate those neurons in a bunch of seconds. So you might say, well, it's very, very slow. yes, if the information wasn't clear, but in those evaluations, the information is encrypted all the time. So the privacy of the input and the result is kept all the time. And this is a very nice achievement from our point of view, because before those results, nobody was able to provide these results for at least, as instance, 50 layers or 100 layers. So we think that now we are showing that, as Sebastian said before, we are trying to, we're showing that neural networks are in the reach of homomorphic encryption. So what we are doing now is we are building our technology inside products, and we already publish a homomorphic library that is accessible on GitHub and can be used. And we will provide more products to allow users to use it in the most efficient and secure way. Our goal, of course, doesn't stop here. The long-term goal is to make the entire internet safer, and by using homomorphic encryption, of course. And to tell you a little bit our idea, I like to show you this, let's say, timeline. Well, 15 years ago, I would say, the standard on the internet was HTTP. So there was no encryption at all in communication, and anybody who sniff your communication will see the information. Nowadays, we use HTTPS, where S stays for secure communication, and the data during communication is encrypted. But as I said before, once it goes on the other side of the communication, it will be decrypted. So our goal is to provide one day what we call HTTPZ, on which we would like to input homomorphic encryption, not only to have encryption during the communication, but all along the way, and having end-to-end decryption all the time in the internet. So this is all I wanted to say. I would like to thank you very much, and I think we can start with the roundtable together with Sebastian.
And now, thanks a lot to Jesus Anserna, and it's his turn.
Okay, so I'm thankful to Luis Alceda and Sébastien Chambaud for the invitation to speak at this meeting, at this roundtable. But I should make it clear that I'm not an expert on artificial intelligence or deep learning or anything like that. So I'm just a mathematician, and perhaps the only reason I've been invited here is because I'm now rather old. So I've now experienced many changes in mathematics in Spain and in the world. I mean, when I say mathematics in my presentation, I will have in mind statistics and mathematics. So I'm not going to repeat again and again statistics and mathematics, but I will use mathematics as an umbrella term to cover them both. Well, it is true that my last paper was published in the Journal of Machine Learning Research. So I'm involved in a sense, but I'm not an expert. And I should also apologize because, I mean, when I received this invitation, I had already committed myself to take part at a meeting in Lumini in Marseille. So I'm in Marseille, and I'm following the meeting here where I spoke yesterday. So maybe I'm not aware of everything that has been said at your meeting in Valladolid. So maybe what I say, I mean, doesn't acknowledge sufficiently things that have already been said and are well known to the audience. After these preliminaries, I want to tell you that I'd like to give two messages. The first message, we are now witnessing tremendous changes in science in the world. Maybe one could say a revolution due to the introduction of a number of new ideas. One of them is artificial intelligence. Artificial intelligence is not new, of course, has been around for a long time. When I was a boy, it was the science in the 60s. I mean, they say that, I mean, the thing that is going to happen in science is artificial intelligence. It was very big, but those expectations didn't materialize. But in recent years, and mainly due to the introduction of deep neural networks, we've seen tremendous advances in artificial intelligence. One uses this, one uses machine learning, one uses data sciences. So there are many things that are new and are very important, and then introducing big changes in science. And this affects mathematics and statistics in the way research projects are financed by the various finances agencies. We're also seeing a change in the demands that on our graduates impose companies worldwide. Also, the curricula of the degrees at the universities are changing. And so all those things are very big changes that are happening. So my first message is that there are many changes and that are happening, and we should be aware of them. And my second message is that as a mathematical and statistical community in Spain, we should not be left out of those changes. We should be aware of them, and we should try to take part of them. And if I'm allowed to give you a counterexample, I will take as a counterexample the way mathematicians accepted computers. In 1970, when I started as an undergraduate at the University of Valladolid, the university already had a computer. But this computer and the mathematicians were disjoint sets. I mean, the mathematicians showed no interest whatsoever in the computer that was downstairs at the Faculty of Science. Of course, this was a big mistake for mathematicians because of jobs for our students, for opportunities to develop mathematics, but also from a purely mathematical point of view, because it's clear that the mathematics in the last 30, 40 years have been very heavily influenced by mathematicians, by computers. And mathematicians, by ignoring the presence of computers, made for a more limited mathematics in Spain. So nowadays, I mean, you always hear mathematicians saying, okay, I mean, computers, this has to do a lot of mathematics, because after all, Alan Turing and von Neumann and so on were mathematicians and were led to the introduction of the computer by using mathematical ideas. But that was not the climate when I was a student in the 1970s. And even to this day, there are colleagues that they say, okay, now mathematics have a new things, computation. But of course, computation was a new thing 50 years ago. So I hope that with machine learning, we don't take 50 years to react in a constructive and positive way. So those are to my messages. There's a big change, and we should be involved in that change. We should be proactive and doing things about that change. Well, just to give you, I don't want to bring you any statistics or anything like that about the changes that are taking place, but I will tell you some indications. For instance, in the journal Science Review, that maybe some of you know, it has an impact index of close to 11, which is much higher than any other mathematical journal. I'm in charge of publishing I'm the editor in charge of the review section. So every year I have to renew the editorial board. And every year I have to discard editors that are based on more traditional parts of applied mathematics, like maybe numerical analysis of dynamical systems or partial differential equations or fluid mechanics, and bring in new editors that know more about complex systems, data assimilation, data science, artificial intelligence, neural networks. Why? Because the number of submissions that we get in traditional areas is decreasing very quickly, and the submissions that we now get are in this new area. Also, enough to look at the jobs that are advertised and positions in universities worldwide. opportunities to PhDs, postdoctoral positions everywhere, you see that there's a big shift. And also, I mean, if you talk to colleagues in the US, even you find that even people who are very well established, they now have difficulties in getting their research financed by the National Science Foundation and other agencies if they stay in the traditional areas, because now the focus of the money is in these new areas. Of course, Spain is not separated from the world, of course, and there are many things being done in the country. For instance, in my own current university, Universidad Carlos III de Madrid, we've had a master on data science for many years now, and there's also now an undergraduate program on data science. And of course, everywhere in the world, mathematicians and statisticians are having difficulties in adapting to the new changes, because when you apply for funds to a research institution, the programs are very made in compartments, and things that are maybe interdisciplinary and so on in every country in the world are more difficult to get finance. If you go in one of the lanes, well, this is algebra or this is partial differential equations, even if your research is not very innovative, you have better chances that if you try to move into a new area and to do interdisciplinary research. But in my opinion, in Spain, we have added difficulties. Well, one of them is this highly bureaucratic system that has been implemented in Spain in the 20 years. We have this ANECA, so everything is bureaucratic. Any changes that you want to make in an undergraduate program or in a master, or the way people are get their accreditation and so on, is very bureaucratic. And bureaucratic things are always very conservative and biased in favor of things as they are, or things as they are going to be in the future. Another big problem with universities in Spain is this existence of áreas de conocimiento that, again, reinforce things that are central to algebra or central to differential geometry, but not things that are interdisciplinary, not clearly, don't clearly fall in a niche. And another big problem in Spain, probably in my opinion, the worst thing about Spanish universities is the complete lack of mobility. People work their whole scientific life at the place where they got their PhD degree. So this is an incentive to going on with the English say business as usual, and try to do what has been done in your environment, in your neighborhood for the last 20 years. And there's very little mixing in the community. So those are the dangers that I see. And now I will take up some of the questions that Sebastian posed in his introduction. But since Professor Bruna has already given many indications, I'll try to be very brief. So some people say that this data science is nothing new, because after all, and against what one often reads, science has always been constructed from data. I mean, Newton started by trying to derive a mathematical proof of Kepler's laws, but Kepler's laws were discovered by Kepler just by looking at data collected by Tycho Brahe and other astronomers. So in a sense, this has always been like this. And many things that now are labeled as data science are just run-of-the-mill statistics. I mean, just statistics as usual. But it is true to say that both to the abundance of data in the modern world, now there are data available everywhere, and the advances in both in hardware and software and computing. Now the changes in data science have moved from what I could, a Marxism, where I could say from being quantitative to being qualitative. So we have a qualitative change in data. So data science, as compared with traditional statistics, is very much focused on prediction, on thinking about the future, whether maybe things like inference are more prevalent in conventional statistics. Also, data sciences encompasses many things that have nothing to do with mathematics or statistics. For instance, and I think we've also heard this from Dr. Chilotti before, things about privacy, legal implications, ethical implications, reproducibility, the capability of explaining things to people, how the results are derived. Those things are very big in data science, and they play a role in data science degree. For instance, if you run a bank and you're a bank manager and you deny a loan to one of your customers because a deep neural network told you that you should deny the loan, you have to explain to her why this loan has been denied. And if you use a current deep neural network, you have no idea what happened in those neurons. What was the concrete point in the data supplied to you by the customer, why this loan is being denied. So those are very big things, many ethical issues that are not nothing to do. Everything has little to do with mathematics, but are not. And of course, data science is very, very much connected with mathematics and statistics, but also with computer science and computation. Yes, after all, deep neural networks are possible because of the many layers that one can now have in the computer. Because neural networks were also popular in the 90s, but then they were so shallow that they were not very useful. Now this new area, data science, neural networks, machine learning, is very much based on mathematical techniques. First and foremost is optimization. Optimization is the basis of the when you train the neural network. So this is very, very important. But then there are issues like approximation theory, which functions can be approximated by a neural network. What are the capabilities, the limits of this? Optimal transport is another area that has become very popular. And here I have to say that in Valladolid, Carlos Matran, I don't know whether he's in the audience, he's been a pioneer of optimal transport and Wasserstein distances in Spain. I also see that Juan Cuesta is connected. So those things are very important. And then another very important area is how to generate samples of a given probability distribution. There's many algorithms, Bayesian algorithms need to obtain samples. And the difference between what's being done now and what was done 20 years ago is that now the dimensionality is very high. Recently, I was asked by an astronomer to generate samples from a distribution, and this distribution was in R to the power 1 billion, 1 British billion or American billion. I wouldn't have thought that what in such a big space one could have a probability distribution. This is what is being done nowadays. So of course, probability and statistics, in particular, higher dimensional probability are very important. But having said that, I hear that people from topology and algebraic geometry are also making contributions, and all those areas are also being used in machine learning. So machine learning has a mathematical basis that gives us opportunities to do research, but also, and as Sebastian mentioned, it will facilitate our research. I'm just going to give you one example. One of our academicians at the Academy of Sciences, Javier Jiménez Sendín, is a worldwide expert in turbulence. And then for many years, he simulates the Navier-Stokes equations to find how turbulence is generated and how it works and so on. So this is an area where the equations to be solved have been known for decades. The Navier equations are well known. Javier knows how to simulate them, and he tries to find phenomena in the numerical experiment. And before, he had to run his codes maybe for 3 months before he had a single simulation. But now computers are more powerful, and he can have more simulations in maybe 1 week that he had before in 3 months. And now he combines this, the codes that he already has, with artificial intelligence, with deep neural networks, in order to combine the results of the simulations with data science to discover new things into it. And he's having a tremendous international success because he's really has identified new things that happen in turbulence simply by applying a combination of computation, well-known, of Navier-Stokes, well-known, but ideas from data science. I don't have time to go into that because I don't want to use a lot of time, but also now artificial intelligence techniques are used to solve partial differential equations numerically, not finite elements, not finite differences, but algorithms that used, and those are particularly useful in partial differential equations where the number of independent variables is high. There are many challenges in artificial intelligence. I think Professor Bruna mentioned some of them. One of them is what happens as the number of layers in a neural network grows. Can we get guarantees of convergence? Can we get error bounds? So there's a lot of theoretical work to be developed. And just to finish my presentation, I would like to, or I've been asked to be a bit practical. I mean, what should we do? First of all, the curriculum of our degrees. Well, I'm personally very against big changes. I think one should adapt slowly in life, not be always conservative, but I don't like revolutions. So I don't want any big changes in anything, any sudden changes. In particular, in Spain, where in our universities, things typically are either prohibidas u obligatorias. En la Universidad Española todo está o prohibido o es obligatorio. And oftentimes things that are today forbidden will be compulsory tomorrow and vice versa. So I want to say you have to change your but I think that it would be good if slowly teachers in our departments become aware at least of the main ideas in machine learning, and when they give examples and when they do their presentations, they show some sensibility to those areas and prepare slowly students for things that will change. Just to give you a very simple, simple instruction. I mean, you all know that in a neural network you have to propagate the gradients backward. This is something, this back propagation that is a key in the success of neural networks is mathematically very simple. It's the chain rule. So next time you have to teach the chain rule, you could explain this to the students, say that this is very important for neural networks, And this not only will make the chain rule to look more appealing to the students, but you also understand it better. If you just don't write the concatenation of Jacobians with it, when you have many functions being composed. And so if you take maybe 5 minutes to explain how the function values, as people in differential geometry would say, are pushed forward by the functions, but the gradients are pulled backward by the function. Well, this is a nice illustration, and then little by little, people will become more familiar. And in order to do that, I think it's very important that the average mathematical professor or professor of mathematics in our departments has some exposure to these ideas. I don't want here to reproduce the situation that I mentioned at the beginning that we had with the computers, where computers have entered our departments not because the professors that were there tried to learn anything about computers, only because they retired. Those that didn't like computers and didn't think highly of computers have retired, and now we have another generation, and this generation has been brought up with computers, and this is the way computers have become more prevalent in our mathematical degrees. I don't want that to happen with machine learning. I think everybody should have a rough idea of what's a deep neural network. I'm not thinking of taking a very complicated course, but just a very simple idea, like in the presentation by Ilaria Chilotti, maybe a bit more. And in order to do that, I think it would be very good if La Gaceta de la Real Matemática Española and similar publications, I think they could prepare a series of papers, not very complicated, very simple things, maybe a series of 3 or 4 papers where everybody could read and get an approximate, a vague idea of what a deep neural network is, because I think that will be very helpful. And so this could be done on paper in the journals. Also, one could think of having 2 or 3 people that are good at doing this kind of thing, that prepare videos, and those videos are made available by the mathematical societies or academies or so on, or also those people could circulate among the different universities in Spain and give very, very introductory courses to this kind of thing. I think those things would be easily done, and maybe could create a sensibility that could foster a change. So this is one area where I think we should do. But I also think that some let's say leaders in our communities, like the presidents of the mathematical societies, should approach the ministries, the government in Spain, the financing sciences, and make clear to them that artificial intelligence and data science and things like that are not disjoint sets with statistics and mathematics. This should be made very clear to those people, to politicians, that mathematics has something to do with it. I mean, we will not be everything, because there are many other communities that have something to say, but we should make clear that the people in charge of science in Spain are aware of this, and this should manifest itself also in that the people that are the managers or gestores of the different programs know that if they get an application from a mathematician to funds that are earmarked for machine learning, well, this is not strange. And I think this is something for the presidents of the different societies, because we should make sure that we can opt to competitive funds by those agencies. And they were not excluded the way we were excluded from computer science when computer science started being funded in Spain. So I would say those are the two things that personally, in my opinion, we should be doing. First, encourage nothing very ambitious, nothing very dramatic. Encourage increasing the sensibility in our colleagues at our departments by having them to understand in very broad terms what's machine learning and what techniques are involved. And this can be done again by publications, but also by preparing videos and giving talks. And then I think we should be proactive and have interviews with people both in the central government and the autonomic governments, and make sure that we are given due access to those areas. Maybe Sebastian, I've been very long with my presentation. If so, I apologize.
Well, I think it was quite nice that you could take a bit more time, and thanks. Well, now I think that from the table, this is as much as we could offer you in the time we had. Now it's your turn. I think that, of course, anyone can comment on whatever they want, but I would ask if you could do an effort to also be propositive about what we should do, okay? Not only give an opinion, but also to urge academies, research institutes, governments, and so on, about what to do so that we, in this decade, that roughly speaking has begun now, after the COVID, that in this decade we can do something of importance in relation to the topic of this table today. It's your turn. Well, you have to go to the microphones, the middle of the room. By the way, you could also send a message. You can send it to me if you want, with whatever questions you could have, whatever opinions, whatever proposals, because I think that the analysis of all the talks, all the proposals must be done afterwards. So when we have all the recordings, we are going to be able to reproduce them, to listen to them again, and then we will prepare a document that would be the conclusions of this table. There have been many ideas, I think, but they have to be put on paper in a way that they can be activated, they can be actioned in somehow. Okay, we will do it as soon as we have all the recordings. Is there any word? So Luis Alceda?
Yeah, so go to try to potentiate the debate since there are no other people. I want to ask a question to the panelists going the direction of something that Jesus and Serna said, which is about training. Do you think that mathematical community should endure serious training of, I mean, apart from working at the level of degrees in mathematics. I mean, at the level of advanced schools or usual tools in research about machine learning and other issues, in particular, increasing frequency of advanced schools, summer schools in this area. What do you think about this training plan?
Jesus, would you like to comment?
Okay. Of course, this will be very helpful, and for instance, in your own case, I'm sure you're preparing at your center seminars and programs and so on. So I think this will happen everywhere, but I think that this has as I see it, a main purpose, and this is maybe to get younger people who are working for for the doctoral degrees or postdocs or people like this to become really more deeply involved into those areas. And I think, I mean, I'm sure, Luis, you have created those programs at the CRM and so on and so forth. And I'm sure also at in Madrid and Bilbao and other big centers, they will do this. But I think this should be, which is maybe more ambitious and maybe more focused on future research. I think this should be combined with what I said, just having in every Spanish university where mathematics are taught, maybe a couple of afternoons where people could be taught in very broad and simple terms about this kind of thing. I remember years ago, Sebastián presented in Valladolid some simple ideas about quantum computing. Well, that kind of thing. Okay, I mean, not everybody is going to work on quantum computing, but I think every professional mathematician should now have an idea, a broad idea about machine learning and so on. The same way, even if you are in statistics or if you are in harmonic analysis, I mean, you should know what a group is or what a field is. I mean, a very basic thing, because I think that will really increment the sensibility. I think I always compare this with what happened with computers. And the problem with computers is that people didn't become involved because they didn't have the sensibility. They said, I mean, without looking into them, well, this is not rigorous, this is not mathematics, this is not theorems. People in those days were being Bourbachists. I mean, what's the structure here? Where are the universal objects in this category and so on? And then they didn't have a sensibility. I think we should be active in promoting a general sensibility in the community.
Yeah.
Hi, so I'm Luis Vega, and for this question or comment, I'm here more as the coordinator of the Red Estratégica de Matemáticas, which is something that you could translate into a strategic network of mathematics in Spain, who is the organization that is behind this workshop. Of course, Jesus, I cannot but insist in your words. I think that, and that's the reason why I also asked yesterday at the end of Alfio Quarteroni's talk, the question, we are in a very in a before and after situation, and for our country and for the mathematics in Spain, there is an opportunity that we shouldn't miss. And this has been in the form, I mean, it has been pretty clear for all the people in the committee of the Red Estratégica, and that was the reason of this workshop, the main reason to make visible to the authorities that there is plenty of people, there are plenty of people in this country already working in all these things, but the main problem is that most of these people are working in small groups at different universities, and then they are not visible from the critical mass locally is small. It is only we have some kind of critical mass which is big in the when you see all the groups all together. I think we have been kind of successful with the Ministry of Science. In particular, we had different interviews with Rodrigo, which was the previous Secretary General, and we were very happy that Raquel Jotti, which is the actual Secretary General of the Ministry, came to the inauguration of the event. And the feeling I got from her intervention and the time we had talking with her was very, very, very positive. And I think we have plenty of things to try to play in that direction. But of course, we need the ideas of we need good ideas because it is not that easy to go from what you want to do it, as we all know. But on the other hand, we haven't been so successful in the other main player in all this business, which is the Secretaría de Estado de Digitalización, that now depends on the Ministry of Economy. And this is much more, that's my feeling, maybe I'm wrong, but that's the feeling I have, that really is, this is mainly run by the people in computer science, and much more from the machine point of view, meaning the really computer. So probably they are not so sensitive at all to the kind of thing we are talking about here, in particular to mathematics. So with this, I'm trying to say, to try to convince everybody who is here that it is our duty. I mean, we have really to say all this kind of, all the arguments you have said and the rest, including the people in the round table, to our local authorities, meaning our colleagues at the departments, in the Faculty of Sciences, at the universities. And for example, yesterday or the day of the inauguration of this, I had the opportunity to talk with the vice-consejero here, and she was very sensitive. Honestly, I'm not so sure that the rector was that sensitive. That was my feeling. But of course, we have to insist in this. It is an opportunity that we cannot miss. And now, Jesus, I cannot avoid the opportunity to tell you that also I would say that the Royal Academy of Science has some room some opportunity to do something in this direction, mainly because in the section of mathematics there are many people in computer science which are part of this group. So we could really try to also play this card of the game. So, well, this is the only sense of my of this small speech I'm saying, that really we are behind all we are trying to push these ideas within the politicians, but it is not easy. It is not easy at all because mathematics are not visible in Spain. We have made altogether a lot of a big effort to make them visible, but we have to insist and as you said, to be proactive. And that's all. Thank you.
Thank you. Well, I think.
May I comment, Sebastian?
Pardon?
May I comment? May I comment on? Yes. Luis, I think, as you know, we agree on this, and I think something very important is to document our points. So when if you as responsible of this initiative go to visit politicians and so on, I think it's important that that one goes with data from what happens in the US or the United Kingdom, and with hard data on on the role that statisticians and mathematicians are playing in those fields in those countries. So it's not. I think it's important not to give the impression that we are like children when they see that other children get a toy that they don't have. I think it's a matter of persuading them that even though other communities in Spain came earlier to those areas, I think statisticians and mathematicians will also have something to play, and this is not something exceptional. This is what happens throughout the world. I mean, I keep going to the same thing. When I got my first tenured job at the University of the Basque Country, I wanted to buy a computer there. And then what happened? I had the money, but then I had to ask permissions from the physicists, because the authorities of the university said, "Okay, you're a mathematician and you cannot be trusted with buying a computer." I mean, I had to go. I still remember the names of those colleagues in physics, and I had to ask them for permission, and because it was taken for granted that those things in those days were for physicists. I think this is something we have to fight right from the beginning, right from now. And one very important is to document with data. One has to collect data about projects in the US, projects in the United Kingdom or Germany, and so on, and the participation of mathematicians and journals, and one has to see in other countries papers that appear in different journals. You see the affiliation, how many authors are affiliated with the math department or mathematical science department, and so on and so forth.
Okay, maybe this is a very broad comment. I would like to ask Luis Alceda, as the organizer of this table, if he would like to comment as well. Yeah, you can comment there. Would you like to comment something? Yeah, okay.
I really don't have essentially new things to say. I have to say that I completely agree with conclusions derived from all panelists, and I share completely the vision, especially the analysis made by Jesus. I think it's very clever, and it gives arguments. And according to what you just said now, that we had to provide to the politicians data and arguments, I think that the arguments essentially are here, and you made a good contribution in the arguments. No, essentially, I don't have anything new. Just what I wanted to do, I accept to talk, just to emphasize that I think that what we have listened today, it goes in the good path, and it's very helpful. I think that we'll prepare, in the line that Luis Vega was saying, we'll prepare a document, conclusions from this roundtable, with recommendations and with data, as you recommend, Jesus, that it will be very helpful in asking for actions at all levels, the level of Spanish government and autonomous governments also. So I think that we did our job with what we were listening here. And I am really thankful, I think in name of everybody, for the opinions that they appear here, and the work you have been done, thinking about what to do and prospective actions. I think that this will be very helpful for us. Maybe I want to add some personal point, is that I have the feeling that in this country we have problems with proactivity of this. During this meeting, I learned some things, and one of the things that I learned is that is in this country where there are problems with artificial intelligence and with the reaction to artificial intelligence. I share completely this vision that when computers appeared, we made a very big mistake, a very global mistake. I mean, we, the mathematicians, this was a very big mistake. And I see that other people are thinking the same. But now I realize that it is in this country where we are a little bit in the queue of this artificial intelligence train. I have seen that in other countries, people have taken more seriously. They have been more proactive. They reacted earlier. And I think that this is a Spanish problem, not an international problem. This is one of the things I have learned here. And so this means that our reaction should be stronger than maybe in other countries.
Thank you. Maybe Ilaria wants also to comment.
Yeah, a very personal maybe opinion on everything that has been said. So I never had the chance to work in Spain or to interact with Spanish university or study in Spain. So my personal point of view is a very external point of view, but I'm very sensitive to the problem that you're raising in this roundtable and in the previous one. So it seems like you want to generate a change and you want mathematics to be listened. And I come from a domain that is very interdisciplinary, if you want. And I think this is very important. I mean, mathematics, to do crypto at least, you need the mathematics, you need the computer science, and the amount of applications that you have is even wider. Like I show you just an application for machine learning, but there are so many. So by nature, the domain that I come from is interdisciplinary. So I see the importance of this. And it's important also to explain to the society, to the politicians, the importance of this and the importance the mathematics has in this. And my opinion is that if you want to generate change, you might act on very, very different paths in many different fronts, I would say. Of course, it's important that politicians listen and government listens because they decide about, they take the important decision, I would say. So for them, it would be necessary to explain, and I totally agree with what Jesus said, to produce material that is simple and that is able to explain in a very efficient way the importance of what you want to transmit, the importance of mathematics, the importance of interdisciplinary collaboration. Also, explain to society the importance of this, and for this maybe speak to journals, have public talks, publish articles, but again staying very easy on the explanation and very focused on why it's important. And there are two other places where I think it's important to take an action, and the first one is on the young generations. So in going to another question that was asked, I think by Luis, the training is important and you have to act on the training of young students. So in university classes, teach mathematics, but also teach other disciplines, show them how mathematics can contribute to computer science, to artificial intelligence, and so on. Allow them to discover it and to be hungry of knowing this and wanted to specialize in this, maybe proposing masters that have already take the direction of computer science, of artificial intelligence with basis in mathematics. And the last point on which I think it's important to act is on the communication between the academy, the research institutions, and the industry, because industry is where the use cases come from, when the problem come from, and university, academy, researchers can really provide the solution. I work on a company where we see real world problem and on which, so we have products and we need research. So we need mathematicians, we need the experts in computer science, we need experts in machine learning, and we need them to collaborate, to interact all the time. So it's important to keep, in my opinion, the communication open and the dialogue between all those institutions. Again, listen also to the necessities of the society, because it's from there that the problems come from, and it's from there that you cannot start to take an action and propose solution and be listened and show the importance of the work you're doing. Again, very external point of view.
Thank you. Well, I think that one of the key words you said and other people is communication. Of course, we are not going to solve the decade from here today. So I think there should be steps to improve, strengthen, or begin a system of communication between all the people interested and concerned. That could be, I don't know, I have a model of a website that people have a design of what has to appear there, and any item that is put in that web is curated, so to speak. Therefore, there is some validation that what you are going to see there or listen is bona fide. I guess that in this movement of cooperation between mathematics and artificial intelligence, it would be very, very important to have such kind of a portal. I don't know, probably the best organization to do that would be la Red Estratégica de Matemáticas. Of course, there is already something going on. I have not looked at it recently, but it would be a very good way of aligning the people into a common purpose of what could be done, who is doing what, and so on and so forth. This is one bigger step. I think that was already mentioned by Jesus, and it would be nice. Now, I think that the closure or the closing of this roundtable will not be today because well, we are doing the closing now, but it will be when we are able to write a suitable document with the conclusions and with the proposals. Is there some other comment or question? So I think that we can close the table here. And
Thank you.
Yeah? Jesus, any more? Okay. Thank you. Thank you, Jesus.